Okay, so in the worksheet, which you'll find in your project, I just came up with a bunch of links. One is there's this basic Sage calculus tutorial. It's kind of weird. It's more of a tutorial about basic calculus that happens to use Sage to illustrate it rather than how to use Sage for calculus. But it was written as a student project 1/4 by a UW undergrad. There's also a book, Sage for Undergraduates. This is a whole book that was recently published by the American Math Society, which you can download from here. And of course, it's a zip file, and then you extract the zip file, and you get a PDF. And here's what it looks like. But if you look at the table of contents, you'll see this has lots of help for things related to calculus. So partial derivatives, gradients, matrices, vector operations, et cetera, et cetera. So it's very much about the kind of math that comes up in calculus and also linear algebra. Plotting techniques, how to make your graphs look nicer, et cetera. So that's another resource. The Sage reference manual itself has very comprehensive documentation about many things related to symbolic calculus. And then there's also a thematic tutorial. There's the Math Association of America has many times had a workshop to train teachers about how to teach using Sage in calculus. And this is some documentation and a tutorial that came out of that workshop. So that's another good place to look for resources. And of course, you can always just type Sage and then something into Google and see what happens. Maybe you'll get an answer on Stack Overflow or somewhere else. Okay, now we're going to do a short, very, very short crash course about symbolic calculus in Sage. So I'll just talk about defining symbolic variables, defining symbolic functions, plotting, I should say differentiating, integrating, and finding zeros. This is not a comprehensive list of topics. We'll do a similar crash course about other topics on Wednesday and Friday. First, when you start up Sage, the variable x, the symbolic variable x, is predefined, but no other symbolic variables are predefined. This is in sharp contrast to how Maple and Mathematica work. So if you just start up Sage cold, and I'll type reset to simulate that, then I think that resets everything to its default state. Then if I type y plus theta, if this works, I might have to click the restart button at the top. Okay, see, it says y is not defined. If you ever see this and you're doing symbolic calculus type stuff, the reason is because when you use a variable and you haven't explicitly declared it to be a symbolic variable, created it as a symbolic variable, you just get a name error. Because after all, we're using Python. There is a mode in at least the Sage command line, which I wrote long ago, which will make it so it tries to run the code. If it gets a name error, then it makes that symbolic variable exist and then tries again. And so it sort of automatically makes variables get created. But it's really not that good of an idea because if you think about it, if you make the slightest typo in a variable name, like let's say you have a variable called theta, and then somewhere deep in your code or what you're doing, you accidentally type like theta 0 or something. Like you make a very slight typo in the name theta. Then suddenly you have yet another variable that just magically appears. And that can really lead to subtle bugs. And that's, of course, how Maple and Mathematica work. So what you could do is, but x, just for convenience, is predefined. So you could say %var and then give a list of variables separated by commas or spaces or whatever, and it will just define those in the scope of your session. And let's do that. And then I'll show, and so once you've defined them, then you can use them, and things work just fine. And there's also some niceness. If you name a variable with a Greek letter name, then it just magically typesets it with that Greek letter. That's why the theta looks pretty in the output. There's just a little table of things like that. It occurs to me we probably haven't done that in every possible situation. I'm curious what happens if you use aleph, a Hebrew letter. Notice that it doesn't typeset it nicely. It just sort of defaults to the name of the variable. A little bit of history, just stepping back for a second from our crash course. So in 2007, Sage had absolutely no symbolic calculus. It was useful for number theory and linear algebra. But if you wanted to teach a class involving calculus, Sage was just a non-starter. You had to use Mathematica or maybe Maxima or something else. And then this UW undergrad named Bobby Moretti, who was maybe a sophomore or a junior, decided he was going to implement enough symbolic calculus so that you could use Sage in teaching calculus. And he worked for about a year on this project. What he did was he made a nice Python API for what symbolic calculus would work like, and then he used Maxima, and I think Maxima only at the time, which is an old computer algebra system, to make it so that things would actually work, albeit slowly. And that's where a lot of this symbolic calculus comes from, and where the design in the API comes from. It's just this one undergrad sat down for a long time. Also, some of the tutorials I mentioned were written by undergrads, and a lot of the functionality beyond what he did initially. For example, there's a units module that was another undergraduate student project, so that you can convert, like meters per second squared and temperatures and pretty much any unit imaginable to any other unit. That sort of stuff is also in Sage. It's just some undergrad just sat down for like 2 quarters and just implemented the hell out of units. So it occurs to me that there's like a not very complete list of mappings from variable names to LaTeX expressions for them. Aleph is clearly missing. If somebody wanted to add this to Sage, it would be a really natural thing to add. So if you're interested in doing that, let me know, because then you could contribute to Sage. By the way, to finish the history, so Bobby wrote all this stuff. At the same time, a guy named Andrei Schertek from Eastern Europe, let's just say, he wrote a pure Python library called SymPy for symbolic calculus. And it's in pure Python. It doesn't use any, or at least initially it didn't use any compiled code, and didn't depend on any big C++ or Lisp-based packages. And it kind of grew at the same time as Sage's symbolic calculus over many years. Also, Sage's symbolic calculus, we rewrote it to be a lot faster than what it was before by using a library called GINAC, which is not a computer algebra system. So here's their website. This is a C++ library designed for high-performance symbolic manipulation, written mainly by physicists in Europe. And we built a lot of Sage's symbolics on top of this. Okay, so things got polished over many years, still getting improved. All right, back to our story. So this is one way. This is another way to define symbolic variables. You can say var, and then this is actually normal Python rather than what you saw before at the % isn't actually Python. It's some special extension. Another way to define symbolic functions and variables all in one go, which I was at UCLA on Thursday interviewing some students, and I learned that there's a major gotcha with this because of a very confused student. But if you type f of, and then in parentheses, and notice this is not valid Python notation, so you put in parentheses some symbolic variables, equals, and then a symbolic expression. Any variable that you've put on the left, like z or anything, even if you haven't declared it in any way before, will get defined. And then you get a symbolic function back, a symbolic expression. And it's also callable in the sense that if you just give it some inputs, it'll evaluate the inputs at those values. So I haven't mentioned, I don't know, myself anywhere, that variable, but I can do that like this. And now I can just evaluate it. See? And now, once I've done this, the variables that we had above are available to use anywhere. So let me tell you the gotcha that so I think I introduced this notation somewhat, sort of a nice shorthand for defining functions. It's pretty natural for mathematicians. There's a really surprising gotcha that I had never thought about until Thursday, which is the following. Watch what happens if you do the following. So say you set z equal to 0.5, you're going to maybe do some iteration to illustrate something like dynamical systems, which is what they were doing at UCLA. So you set z equal to 0.5, then you define this function. What happens is right after you define the function, it makes z the symbolic variable z. And then afterwards, when you do print z, you just get z out, rather than 0.5, which could be very confusing, especially if your next step were to be to evaluate f at z multiple times iteratively, because you'd suddenly just get a huge, massive symbolic expression. So you kind of kill it, you run out of memory, and it doesn't work at all. And nothing will evaluate. So the gotcha is that this line whacks the previous definition of z. Okay? It's similar to the gotcha with list comprehension, where you do the square brackets x something for x in range, and then suddenly x is redefined after you do the list comprehension. But it's even worse because you really don't expect this to redefine z, because in Python, if you were to do this, this would not redefine z. Watch. So I just want to warn you about that. This is definitely surprising behavior potentially. That said, this morning when coming up with your homework set, John and I typed in a lot of symbolic calculus type stuff in order to make up all the problems and also to write solutions. And this behavior is extremely natural and useful. It's kind of what you really want. So for better or worse, it's really nice that right after you define a symbolic function, that you can use any of the variables that you mentioned right there. It's just like when you're working interactively, it's extremely convenient. So I'm kind of torn whether, well, I'm just a little torn about this. In any case, gotcha. Hopefully you will never run into this problem because I told you about it. I'd actually never hit this myself, but I saw somebody very confused for a while about this. Okay, some other things. So plotting, you've done this before, but if you define a function, you can use plot. The plot function has a bazillion options. As you can see, like you can pass in a color, such as chartreuse. If you ever wonder what that looks like. But you can also pass in an RGB color and other color spaces. You specify a thickness. Z order, that's one thing for plotting that you may get really frustrated if you're trying to draw a plot with multiple elements in it, and one of them is covered by another one, and you're like, oh, maybe I'll just change the order of plus or something to... So just to emphasize, I mean, that might not make any sense if you haven't seen a little more complicated plotting, but if I do, I'm going to put hi there, class, as a text element at position 2, 1. Okay, so we should suddenly see some text right here. And notice we do. Oh, that's kind of a bad example. I need to make it on top of the green line, so I need to go up a little bit, maybe 2, 6. I want it to overlap. Yeah, so what if I really, really wanted the text to be on top of the green line, not below it? So the solution to that problem is not to try to change the order of adding right here. That has no impact on what's on top of what else, which is reasonable because addition should be commutative. It shouldn't matter in which order you add. Of course, programmers don't think that way, which is why a string plus another string is the concatenation of the two strings, but if you add in the other order, it's different. So anyways, a little pet peeve, but in you can do z order, and that will specify the order in which things are rendered. And notice now the text is on top. So if you're ever trying to draw a plot and you want one thing to be on top of the other, use z order. Yes?
So like z is on the z-axis?
You can think of it that way. There you are. But there's a huge number of options to the plot command, and you can see them by, put the cursor after the open parentheses and hit tab, and you'll see a big list that comes up. I really wish this was syntax highlighted. Some of the interesting stuff is there's really sophisticated, like adaptive recursion. So it'll take the plot, it'll take the function that you want to plot on some interval, and then it will choose random points. Well, it'll divide the interval up into equally spaced spots, and then it randomly perturbs all the points somewhere, just a little tiny bit. So that if your function is some there's these functions you can make that, there's 0 at all the multiples of some value, and so when you try to plot them, it just looks like 0, but really they go all over the place. So this tries to avoid that by randomly changing a little bit all the inputs. It then evaluates the function at all these points, and then anywhere where there's a significant change from one point to the next, it will evaluate at a bunch of points in there. And it will keep doing that until there's very little change from one point to the next, up to some level of recurrent, up to some level of detail. That's what all this stuff is about. And actually all this stuff was written, so most of this functionality for a plot that makes it really, really complicated, things like, there's a lot of stuff for grid lines and all kinds of other stuff. but it was mostly written at Sage Days 9 up at Simon Fraser University a couple of years ago by a bunch of grad students, in case you're curious. But there's a lot of stuff there. What? Yep. So if you have any 2D graphics elements at all that you've made in any way, like a plot, some text, a point, a line, polygon, you just use plus, and that superimposes them on top of each other. So that's a way to combine multiple elements. That's what I did right here. I let G be the output of this plot, and then I did plus. And if you just show that, if you just like put the plot all by itself on a line and evaluate, that just displays the plot. Alternatively, you can explicitly say show of the plot, and it will appear. If I do this, it will be exactly the same if I do show. It's just more explicit. There's also a save command, which you know about already, because you use that to save plots to PDF in order to put them in LaTeX documents. Okay, moving on. We're doing time, good. So you can differentiate a thing. It's usually best to explicitly say what the variable is, but this is kind of like the first thing you ever do in, I don't know, pre-calculus or calculus or whatever. So you can differentiate a polynomial. Let's define a function and integrate it. So that's another thing, symbolic integration. So sine times cosine times tangent, and then integrate with respect to x, and here's what we get. And then we can differentiate the result, and there's not exactly what we started with. So it's two different expressions for the same function. So the input is sine of x cos x tan x. I find some integral, and then I differentiate that. And the result by calculus has to be off of the original one by, well, nothing. It has to be the original one. So let's check. So if we take the difference, you get this. And as usual, I'm using show to make it so it prints really nicely. And of course, you can also do LaTeX, as you know, and you can do show math as tech commands if you ever want to copy this into a tech document. And you have this k. This should be 0. And so let's try plotting it. So when you plot it, it looks like that. What's happening here is it chooses a bunch of random points between 0 and 1. It replaces x by some double precision floating point number, and then evaluates that expression. And the result is extremely small. It's on the order of 10 to the minus 17. But it's still like sort of randomly bounces around. And when it draws a plot, it rescales the axes so that they go from the smallest value that you saw to the largest value that you saw. So these axes aren't at all square. Like this is an incredibly small range. This means 1 times 10 to the minus 16. So you have to really look at what the range is. And so this looks close to 0, but it isn't quite 0 numerically. But you can do, there's a whole bunch of simplify commands. So if I do k is a symbolic expression, which maybe it was only defined in the previous session, so I'm going to reevaluate this stuff. Okay, so I've reevaluated k. If you do k.si tab, you'll see that there's a whole bunch of different, I'll zoom in here, simplify functions. And what these do is they take your symbolic function and they convert it via a very fast method to a symbolic expression that's equivalent to it in maxima, which is an ancient but very powerful computer algebra system. And then they apply the corresponding simplification rules. So there's a number of simplification rules that use different types of things, like trig simplifications and so on. And there's a simplified full that just kind of tries everything. And then you'll give back something. It'll take the result in maxima and then it'll convert it back to Sage. So let's see what happens in this example. We do simplify, whoops, what just happened? I think I just closed my, I closed my thing. Oh, here it is. Okay, so I do k.simplify full and I get back 0, which tells me that the difference Well, basically, I'm just checking that calculus works, or that the integral is as claimed. Okay, and thus concludes your crash course in symbolic calculus using Sage. Again, it's really deep under the hood, but at the top level, you just make symbolic functions and do various things with them. Maybe the last thing is if I do just k.tab, you'll see the things you can do with the symbolic expression. And there's, of course, a very, very long list of things that you can do. Like Taylor series and all kinds of other stuff. Okay, so now what we'll do next is you'll start working on your homework assignment, and I'll come around with John and answer questions. Okay? Unless you have any questions immediately. And I'll stop the screencast.